Welcome in the next lecture. So in the last lecture we were discussing about the Fourier series properties. Okay, so what we have discussed up till now was the part of continuous time Fourier series. Okay, now we will be discussing the next topic, which is the discrete time Fourier series. Okay, so you know that a discrete time signal, which is represented by xn, it is periodic if it follows this condition. Okay, where this n is called the period of the signal. Okay, so this is some this may be some integer. So the smallest value of this n for which this equation holds true will be called the fundamental period of the signal. Okay, and the fundamental frequency then will be equal to omega naught equals to 2 pi by n. Okay, so a periodic signal, that is this xn. Okay, so if this is a periodic signal, then it can be represented by a discrete time Fourier series, which is made up of different either sine or cosine components or exponential components. Okay, so we have already discussed these two different forms of Fourier series. One is called the trigonometric, other one is called the exponential. So if it is the trigonometric Fourier series, it will be containing the sine and cosine terms, and if it is the exponential Fourier series, it will be containing the exponential terms. Okay, so this signal can be represented by a discrete time Fourier series having this fundamental frequency omega naught equals to 2 pi by n and its different harmonics. Okay, so this complex exponential, that is this e raised to the power 2 pi by n, where this part actually is representing the frequency, the fundamental frequency. Okay, so this if this complex exponential will be periodic with this value of n as its period. Okay, so the complex the exponential Fourier series will consist of different exponential terms, like if I give you example, e raised to the power j0 n, then e raised to the power plus minus j omega naught n, e raised to the power plus minus j times 2 omega naught n, and so on it can be. Okay, so for any value, let us suppose k, so e raised to the power j k omega naught n and so on. So there will be a set of all these discrete time complex exponential signals, obviously that are periodic with this value of n as its period. So we can write this set as e raised to the power j k omega naught n, which can further be simplified if you put the value of omega naught as 2 pi by n. Okay, now here this k can have different values. Okay, starting from 0 to plus 1 plus 2 in the positive direction, then in the negative direction as well, minus 1 minus 2. So all these signals, although they have the fundamental frequencies that are multiples of this 2 pi by n. So you can see that the first term, which is this let's suppose e raised to the power j0 n, then the second term, which is e raised to the power j omega naught n. Okay, it is having the fundamental frequency omega naught. Then this term having the fundamental frequency, which is twice of omega naught, then k times omega naught. Okay, so the fundamental frequencies, you can see they are the multiples of this 2 pi by n. Okay, and these components are harmonically related with each other. So the discrete time signal, which is this xn, it can be expressed in the form xn summation over this k xk and phi kn, isn't it? So again this can just be simplified to xk e raised to the power j k omega naught n, and if you further put the value of omega naught, then it will become e raised to the power j k 2 pi by n. Okay, so this signal can be represented in this form. Now if you recall one important property when we were discussing about the exponential signals in the first unit, that the discrete time exponential signal whose frequencies are separated by 2 pi, they are identical. Okay, so if you remember that we discussed that, let's suppose that there is an exponential whose frequency is separated by 2 pi, so that will be equal to this e raised to the power j omega naught n. So you can see that this exponential is having the frequency omega naught, and this exponential is having the frequency of omega naught plus 2 pi. So both these signals are equal, because this can be represented in this form, isn't it? You can just simplify it. You can just open this bracket. It will be e raised to the power j omega naught plus e raised to the power j 2 pi n. So j 2 pi n will be 1. So the only thing that will remain is e raised to the power j omega naught n. Okay, so what I told you, that the discrete time exponentials whose frequencies are separated by 2 pi, these exponentials are identical. Now just by utilizing this important property, you can see that the set of exponential signals which we just write down in the previous slide, this phi kn. So in this phi kn, you can see that for phi 0n, let us suppose that it is e raised to the power j 0 2 pi by n, and this phi 0n will be equal to phi n. So you can also see from here okay, because both these exponentials will be equal. Similarly, if you calculate phi 1n just by utilizing that very expression of phi kn, so it will be e raised to the power j 2 pi by n, and if you calculate phi n plus 1, then it will be e raised to the power j n plus 1, and in the multiplication it will be, let me just erase this, 2 pi by n. So if you will simplify these two exponential, that will be equal. So what I meant to say, that this phi 0 term is equivalent to phi n, this phi 1 term is equivalent to phi n plus 1, or in general we can just write down that whatever phi k n will be, this phi k plus n will be similar to it. Okay, so you can try for different values, this will be equal. Now what is the physical interpretation of this expression? It is that the first harmonic, that is this first harmonic which is represented by phi 1, it is identical to the n plus first harmonic, isn't it? Similarly, the second harmonic will be identical to the n plus second harmonic, and so on. So you can infer one important thing from here, that there are only n independent harmonics, this capital N. There are n independent harmonics and their frequencies range over an interval 2 pi. Now this means an important conclusion about the discrete time Fourier series, which is that this discrete time Fourier series has finite number of terms. So finite number of n terms there will be. So this much number of terms will be present in a discrete time Fourier series. So you can write down this thing here, that the discrete time Fourier series has finite number of terms. Okay, and what is that finite number? It is equal to this capital N. So this is the difference of the continuous times Fourier series with the discrete time, that although in the continuous time there is no limit in the number of terms, in the discrete time case the Fourier series will have finite number of terms, that is n. Okay, so this means that you can choose any n independent harmonics e raised to the power j k omega naught n. Okay, so there can be different intervals, like from 0 up till n minus 1, both are included, or the second the other interval can be this. Okay, or one more alternative can be this. So any of these, or there can be any other choice also which can be there. Okay, so every one of these sets, these three I have written, and any other set which you might just write by using this concept. So every one of these sets will have the same harmonics, although the order can be different, but the number of terms that will be n. Okay, now using all these things which we just discussed, now we can write down the Fourier series of a periodic signal xn, that is consisting of n harmonics. Okay, so it can be written as summation k equals to, inside brackets this n, xk e raised to the power j k omega naught n. Okay, now this summation sign is actually representing the summation over any range of consecutive k, exactly n in length. Okay, so this is representing summation over any range of consecutive k n in length. Okay, so this is what this representation is telling you, that the length is n. So any set of values you can choose. Okay, so this is the discrete time Fourier series. This expression is the discrete time Fourier series, and the coefficients uh, can be obtained by using this expression. So in this way you can obtain the coefficients of this discrete time Fourier series. Now let us consider a problem based on this Fourier series. There is a signal which is written as xn equals to 1 plus sine 2 pi by n times n, or you can just put this n also inside this bracket, plus 3 cos 2 pi by n plus cos 4 pi by n plus pi by 2. The question is, determine the Fourier series coefficients okay, and plot the magnitude and phase spectrum. Magnitude and phase spectrum. Okay, now quickly we shall start the solution. So first let us simplify this expression. We can write it in this form, in the form of omega naught. So all things are same, only we have just put the frequency here. Okay, now from here you can just write it down in terms of the different complex exponential signal. In the same way, I think we have utilized this thing in some previous problem as well. So just utilize this same thing here also. So sine can be written as e raised to the power j omega naught n minus e raised to the power minus j omega naught n upon 2j plus 3 e raised to the power j omega naught n plus e raised to the power minus j omega naught n divided by 2 plus e raised to the power j omega naught n plus pi by 2 plus e raised to the power minus j omega naught n plus pi by 2 and divided by 2. Okay, so now if we further simplify it, it can be written in this way. Combine the same terms. E raised to the power j 2 omega naught n, and one more term e raised to the power minus j pi by 2 multiplied by e raised to the power minus j 2 omega naught n. Okay, now whatever expression you have obtained, now you can compare it with the standard form, that is xn equals to x naught plus x1 j omega naught n plus x minus 1 e raised to the power minus j omega naught n plus x2 e raised to the power j2 omega naught n plus x of minus 2 e raised to the power minus j2 omega naught n. So you can just identify with this exponential term that what terms of the Fourier series can be written here and compared with. Okay, so you have to compare these two equations which you have written, that is this equation and this upper equation. So by comparing this, you can get the value of x naught as 1, x1 can be 3 by 2 plus 1 by 2j, or it can be written in some more simplified way as this: x minus 1 can be written as 3 by 2 plus 1 by 2 j. Okay, x2 will be 1 upon 2 times j, and x of minus 2 will be minus 1 by 2j. Now the magnitude and phase spectrum which you have to plot. So the plot of this magnitude of xk versus omega, this is called the magnitude spectrum. Okay, and the plot of this, let's say, angle of this x omega versus omega, this is called the angle spectrum or phase spectrum. Okay, so you have to plot this magnitude as well as phase spectrum here. So the magnitude of different harmonics can be just written down from the values of the coefficients which we have just obtained in the previous step. So the magnitude of x1 and the magnitude of x minus 1 will be equal. That will be equal to root 10 by 2, and the magnitude of x2 and the magnitude of x minus 2 will be equal to 1 by 2. Okay, similarly you can also find the angle. It will be 0, and angle of x1, it will be minus 10 inverse of 1 by 3. Then angle of x of minus 1. So you can just obtain these very easily from that complex form which we have written for different coefficients. x2 will be pi by 2, and x minus 2 will be minus pi by 2. So you have obtained these values. Now you just have to plot this. So first I will draw the magnitude spectrum. So let me just draw this. So this will represent the magnitude. Okay, so x0 is 1, so this will be 1. Okay, this will be 1, and x1 and x minus 1 both are root 10 by 2, so this will be somewhat greater than 1. So you can just plot it here. So if it is 1 and it is minus 1, So this will represent root 10 by 2, it will be same. And then for x2, which is 1 by 2, so it will be less than this 1. So this is 2, this is minus 2, and they both will be equal to 1 by 2. Okay, so this is x0, this is x1, this is x2, this is x minus 1, this is x minus 2, the magnitude. Okay, so you can also just cross verify it. Now same spectrum can be seen at n distant locations. Okay, so if it is 0 here, then at n it will be same, that is 1. Okay, and similarly then the next location will be root 10 by 2. So this will be 10 by 2, this will be 1. Okay, so from here to here, this will be n samples apart. Okay, so this will be same, so this can be symmetric, so you can just plot this. And similarly here also, in this region also, if it is this 1, this is root 10 by 2, and this is 1 by 2. So this is root 10 by 2, this is 1 by 2, this is 1. So something like this. Okay, so this represents minus n. So this is called the magnitude spectrum. Okay, this is the magnitude spectrum for this problem. So similarly you can also plot the phase spectrum for it. Okay, so let us just draw the phase spectrum, that is angle. Okay, so since x0 is 0, so there will be no value here. x1 is minus 10 inverse of 1 by 3, so whatever value it comes out to be, it will be in negative direction. Then x2 will be pi by 2, so here it will be, let's suppose it represents pi by 2. Okay, so this is 1, this is 2, and similarly x minus 1, which is 10 inverse of 1 by 3, so whatever this magnitude is, that will just be in opposite direction here. This is at 1, sorry, this is at minus 1, this is at 1, and x minus 2 is pi by 2, so this will be in negative direction. This is at minus 2. Okay, so this is how phase spectrum will be plotted. Now same thing you can do in this phase spectrum also. You can just reproduce this waveform at n distances apart, in the positive as well as in the negative direction. Okay, so same waveform will be here also, like we have done in the magnitude spectrum. Okay, so this is the phase spectrum. Okay, so this is how the problems related to the discrete time Fourier series are solved. Now this is all for today. We'll discuss the next topic in the next class. Thank you very much.